Good evening. Welcome to the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. And what I'm going to talk about tonight is what we call lot by lot acceptance sampling. Now, I work in the field of construction and we deal with quality control. Now, if you're working in the manufacturing industry, you also deal with quality control. Now, what's quality control? Quality control is where you basically take a sample of the material that you're either assembling a new product or you're placing for infrastructure, such as a road, such as a building. Now, when you are dealing with manufacturing and construction, what you're doing, you're taking a sample and you're testing it to make sure that the design is correct. And when the design is correct, that sample is accepted. I'm going to share my screen and we're going to go to what we call this is lot by acceptance sampling. Now, here we're going to cover the role of acceptance sampling in modern quality control systems. We're going to understand the advantages and disadvantages of sampling. We're also going to understand the differences between variable and attribute sampling. We're going to introduce single, double, and sequential sampling plans. We're going to understand what OC curves are and how to use them. And then we're going to introduce different types of sampling structures. Now, in our opening statement, it may seem illogical to discuss a topic whereas we're going to find out we are willing to accept a certain percentage of bad parts. Now, most quality management systems are focused on achieving high levels of quality nearing 4, 5, and 6 sigma, which is 3.2 defects per million. Now, these are instances, though, where achieving quality at those levels would be cost prohibitive. Just think about produce in a supermarket, or if you buy a bag of grapes and there are a few that you would not eat. And what do? Well, we don't reject the whole bag. We may reject some of them. Also, talk about the cost to prevent those few bad ones that would far exceed the willingness to pay for that level of quality. And then consequently, we are prepared to accept some defective product based on our willingness to pay and the severity of the defect. Now, basically, what we're going to get into here, when we deal with Sigma, we're dealing with manufacturing. Now, it is situations such as this where we need to ensure some acceptable level of quality but are willing to accept some non-conforming material that acceptance sampling fits into our quality management system. Now, what we're going to do, we're going to discuss acceptance sampling, but I'm not going to dive as deeply into the topics because there is a lot to cover in acceptance sampling. So I'm just going to give you an overview because my goal is to show you how to gain awareness of what acceptance sampling is and how it works. Now, acceptance sampling is concerned with the inspection and decision making in regards to product and material quality. Of course, once upon a time, it was common for producers to inspect materials when they were received to ensure that the product met the customer's requirements. Now, the process consisted of inspecting shipments and accepting or rejecting lots based on specific characteristics deemed important by the customer. In the 1930s, we began to apply statistical concepts and techniques to acceptance sampling to help with determining how much to sample and when to accept and when to reject. Now, acceptance sampling has become less prevalent in recent years, in large part to the wide acceptance and implementation or correction, that's implementation of quality management systems. Again, acceptance sampling has become less prevalent in recent years, in large part due to the wide acceptance and implementation of quality management systems. Why? Because it's still a role that acceptance sampling plays. However, in certain industries and situations, it's more common than others. Let me give you an example. Because acceptance sampling, although you don't see it too much, it still has a role to play in certain industries and situations. Example, acceptance sampling is more common in chemical industries and producers that utilize a continuous flow manufacturing strategy where materials are produced in lots. Now, I can tell you, when I work in construction, we don't produce asphalt in lots. However, when we place asphalt, we have base, intermediate, and surface. We use lots and sublots. Why? Because we're taking that sample and we're testing it to make sure that every time we put down asphalt, it meets the needs of the mixed design. That's called acceptance sampling. Now, even in these situations, customers often require the producer to do the testing and submit the certified results of the lot upon receipt. That's exactly what we do with asphalt. Once we take the tests, we grab the samples and we send them to the contractor and DOT to test them. And then we get the test results. That's basically how they do it in industries that involve manufacturing or chemicals. Now, in this case, it becomes a review and verification of documentation more than acceptance sampling. Now, regardless of who does the testing, you will still need a plan of how much to test and when to accept or reject. Now, the important aspects of acceptance sampling. This is what you need to know. Acceptance sampling typically involves the sampling of a lot material and then making a decision about the disposition of the lot based on the sampling results. It is the purpose of acceptance sampling to make a decision about the disposition of a lot, not the level of quality of the lot. Also, acceptance sampling does not ensure a level of quality control. Why? Because you are making decisions about a large group of items or amount of material based on a small sample. That's why sometimes we can't use statistics, because we're using a small sample trying to represent something very large. Now, as we learn, samples should resemble their populations, but there is always range that describes where the actual mean or variance falls within. Now, in acceptance sampling, there are instances where you will accept bad material. It's called type 1 error, and you can reject good material. That's type 2 error. So the most effective use of acceptance sampling is not as an inspection tool, but an auditing function that serves to verify processes or the process controls are working. Again, the most effective use of acceptance sampling is not as an inspection tool, but an auditing function that serves to verify process controls are working. 3 approaches to lot sentencing. Number 1, accept with no inspection, commonly used as a result of quality management systems and SPC controls at the supplier. Now, what is SPC? SPC is known as statistical process control. This is when you get into all of the charts based on statistics. Now, there's also 100% inspection, which is costly and not commonly used or effective unless absolutely necessary. Also, acceptance sampling is a representative sample which is tested and decision is based on result. So testing and number of non-conforming. Again, when we deal with acceptance sampling, we're basically taking a representative sample and we're going to make sure that sample is tested. And the decision is based on result. So testing, and we also deal with the number of samples that are non-conforming. Now, here's when acceptance sampling is most useful. This is when testing is destructive. This is where we also have 100% inspection cost, which is very high. We also deal with acceptance sampling being useful when inspection error rates are high. Also, when quality levels are good, but not high enough to warrant an inspection. Also, we use acceptance sampling where there are potentially serious product liability risks with a product. Airbags is a good example. Now, the advantages and disadvantages of sampling. Well, comparing acceptance sampling to 100% inspection, we will find the following advantages. The results in less inspection and consequently less cost. Also involves less handling, and as a result, we have a reduction in damage and cost. Another advantage is it's basically appropriate if destructive testing is required. Also reduces the amount of inspection error. And then something that's very important. The rejection of lots is a motivating factor for suppliers to improve their processes. But as with every advantage, there's a disadvantage. So here's what happens when sampling doesn't work. Well, acceptance sampling is subjected to accepting bad lots of material. Acceptance sampling is a snapshot of the process and provides less information. Acceptance sampling requires documentation and procedures of how to conduct and what to do. It requires a more detailed understanding of customer quality requirements. Types of sampling plans. Well, when we deal with SPC, which is statistical process control, there are what we call control charts. So as with control charts or control charts sampling plans, they can be categorized into variable and attribute. So in addition, we often discuss sampling plans in terms of single sampling plan, which is one sample of n units. It's selected at random. And we have disposition. It's determined based on C number of defects in a sample. Then there's the double sampling plan, which that's an initial sample that's selected and evaluated in terms of C number of defects. A decision is made based on this sample to 1, accept lot, 2, reject lot, 3, take an additional sample and combine information with first to make a decision. Then you have multiple sampling plans, which is basically 2 or more samples used to make a determination about lot quality. And when we deal with random sampling, a key to acceptance sampling is ensuring your samples are randomly selected. So, as with samples for control charts, acceptance samples, it must be randomly selected to ensure they are representative of the population, or we can say lot. Now, all of this goes back to our normal curve and the central limit theorem, which simply says that the distribution of random sample averages will follow a normal curve, and we can use sample averages and sample standard deviations as estimates of population means and standard deviations. And you're dealing with statistics. This is when you have to know how to do the statistics. Now, there are different techniques that you can use to ensure random selection. Number one, assign a number to each unit and devise a random number scheme to select. Number two, stratify the lot. In the event of bulk materials, you might divide the container into layers and cube sampling from different areas. Now, as for any testing, there are guidelines you have to follow. So basically, an acceptance sampling plan is a statement of the sample size to be used and the associated acceptance rejection criteria used to sentence lots. There's an acceptance sampling scheme, which is a set of procedures consisting of acceptance sampling plans that include lot sizes, sampling sizes, acceptance rejection criteria, generally the number of defects per sample, and acceptance sampling procedures, because there are a number of different acceptance sampling procedures. And basically, if you have the book, and that's statistical process control, it lists several approaches dependent upon the objective that you're trying to achieve. Now, single sampling plans for attributes. Now, the key variables for a sampling plan are n equals lot size. This would be the number of units in a lot. That's capital N. Lowercase n equals number inspected. This would be the random sample of units selected from the lot. Uppercase D equals number of non-conforming units observed. This would be the different number of defective units you can find out if your sample N, or your sample N. Then you have lowercase c equals max number of observed defects. And this is the maximum allowable number of defects you can find and still accept the lot. And number two, it's based upon this information that we can develop what is known as the OC curve, or operating characteristic curve. And once we have the OC curve, we can make a determination about the likelihood of accepting or rejecting lots. Now, as you see, the operating characteristic curve provides you with a plot that tells you the probability of accepting a lot versus the lot fraction defective. So across the x-axis, again, across the x-axis, we have a proportion defective. The y-axis provides us with the probability of acceptance. So referencing the curve allows us to predict the probability of accepting a lot based on the proportion of non-conforming units. So, for example, if you have a proportion defect of 0.02, then you are 80% likely to accept the lot at this defect rate based on a sampling plan of n equals 89, c equals 2. And here's what the curve looks like right here. This is your OC curve. This is your probability of acceptance, and your probability of acceptance is 80%. That's 0.8 right there. And he said C, 0.2. Well, everything must intersect. You have n equals 89, c equals 2. And here's your curve right here. This is your lot fraction defective P. And they give it to you at 0.02. Then you're at, now you go up from 0.02. Now, how did I get 80%? I go 0.02 and I intersect right here on this point on the curve, and I go over to 0.8. 0.8 is 80%. That's where they get that from. Again, this is how you do statistics and interpret graphs. It gave you a situation where if you have a proportion defect of 0.02, you're likely to accept the lot at 80%. And I'll show you how they got that. And this is based on a single sampling plan, N equals 89, C equals 2. Well, here's 0.02. Here's the lot fraction defective. 0.02 as you were given. Now, how did I get the probability of acceptance at 80% or 0.8? Well, if I draw a line up to this curve, right here on this curve, I'm going to intersect this curve at 0.8, which is 80%. That's how they got that. Now, the OC curve provides us with the probability of accepting a lot given an observed number of defects. So we can calculate the probability of acceptance P using the formula. Again, here's the formula right here. Now, effect on N and C on OC curves. As you vary the sample size and max number of observed defects, the shape of your OC curve will change. You can affect the discriminant power on your sampling by adjusting N and C. Essentially, your goal is to find an acceptable plan that protects the customer without adversely impacting the supplier at an acceptable inspection cost. This is generally communicated through the acceptable quality level AQL. The AQL, which is the acceptable quality level, is the poorest level of average quality of the supplier's process that the customer would consider acceptable. So basically, AQL is the average value, and so it does not represent individual lot sizes. But you do have your LTPD, which is your lot tolerance percent defective. That is the poorest level of quality that the consumer is willing to accept in an individual lot. Now, here again, here are your OC curves, your sample sizes, and you can adjust them to make them look any way you want them to. And it's based on the sample size. And again, we're dealing more with statistical process control. All right, type A and type B OC curves. So far, the OC curves we have constructed are known as type B OC curves. Why? Because the assumption of a type B OC curve is that random samples come from a large lot. Again, the assumption of a type B OC curve is that random samples come from a large lot, essentially infinite, or the random samples come from a stream of lots from a process. So under these conditions, a binomial distribution is the basis of our probabilities. Again, under these conditions, a binomial distribution is the basis of our probabilities. Now, a type A OC curves assumes that you have a sample from a lot of a finite size. This drives a different distribution. So the hypergeometric distribution, again, this drives a different distribution, which is the hypergeometric distribution. So if the lot size is 10 times the sample size, then the two curves are approximately equal. Now, unless you're working with small lot sizes, say for trials or R&D, you probably do not have to worry too much about type A curves. Rectifying inspection. When a lot is rejected, it can often be reworked to bring into acceptance. This is generally done with 100% inspection. Note, we are inspecting the lot 100%. So typically, if you have a non-conformance, you might need to sort 100% of the lot or perhaps some of the specified number of lots before returning to your regular sampling plan. Why? Because this is still less costly than 100% inspection of all lots on an ongoing basis. average outgoing quality. So basically, when a lot is rejected, it can often be reworked into acceptance. So just with any inspection, rectifying inspection is a process that corrects lot quality when you have a rejected lot. So what it is essentially we are inspecting units in our sample and replacing bad units with good ones. We are not necessarily inspecting and replacing units in the entire lot. Instead, we replace defects in the sample. This serves to reduce the number of defects in the lot. So we're using what we call AOQ. AOQ is average outgoing quality as a means of evaluating a sample plan that utilizes rectifying inspection. And then AOQ can be thought of as an average of the proportion before and after rectifying the inspection. Then we get into double, multiple, and sequential sampling. So there are variations of the single sampling plan that will allow you to do further inspection to determine whether or not a lot should be rejected. So I am not going to go into detail of these plans, but you should be aware of them. They include double sampling plans, multiple sampling plans, and sequential sampling plans. Now, when we have a double sampling plan, it involves sampling from a lot, and based on the results of the sample, the lot is rejected or accepted, or a second sample is inspected and the decision is based on the combined samples. Double sampling plans do have the advantage of potential lowering inspection costs than single sampling. This is true in all cases where the lot is accepted in the first sample. And it even holds true for the second sample inspections, providing that quality control levels are sufficiently high enough to avoid excessive second sampling scenarios. And also, double sampling has the advantage of more complex procedures and the added handling and storage of samples and, of course, lots. Now, the double sampling plan, again, multiple sampling plans are extensions of double sampling plans where more than 2 samples can be required to sentence a lot. Now, at the completion of a sample, if the number of defects in a sample is less than the accepted number, lot is accepted. Again, at the completion of a sample, if the number of defects in a sample is less than the accepted number, then the lot is accepted. Now, if a number of defects equals or exceeds the rejection number, the lot is rejected. If the number of defects equals or exceeds rejection number, the lot is rejected. Now, in between these values, you continue to sample up to 5 samples, at which time disposition must be determined. Now, sequential sampling is another variation of double and multiple sampling plan. I doubt you will run into this, but be aware that there are a variety of multiple sampling plans that have value in select situations. Now, again, what I did was give you an overview of random sampling. Now, what you just dealt with is something in statistical process control. This is when you use control charts. This is when you go into DEMIAC. But again, in construction, we also do random sampling, and we use lots and sublots. We basically take a sample at a certain tonnage by using a random number. And anything that's random, there's some statistics involved. And this is why I always tell you, when it comes to sampling, you want to take a sample that's going to be representative of a population, a material. But remember something, that sample is only a representative. It's not going to tell you everything. You're just utilizing it for a test. And when it comes to any material, you're doing R&D in manufacturing, or if you're testing chemicals, you want to make sure that you're meeting the standards, because everything that we deal with, whether it's construction, chemicals, or manufacturing, it's a product. And what we're trying to do, trying to meet customer satisfaction. Because if your product always fails, you can't put it out. And when you can't put out a product, you're not going to make money. If your product is good, people will buy it. But remember, when it comes to sampling, lot sampling is still important. And always remember that a sample is a representative of a large portion of material that you are using to design a project, or you're making a chemical, or you are putting together or assembling a computer. You need testing, whether it's for manufacturing, chemistry, or construction. That concludes this topic on lot by lot acceptance sampling. If you like what I just presented, please comment, share, and subscribe. And if you are looking for some social and political content, check out my main channel, the 411 Talk Zone Radio Show, also on YouTube. Now, if you can't find the 411 Talk Zone Radio Show or the QCIS channel here on YouTube, check both of those channels out on Twitter. And for the QCIS channel, I take it one step further, since it is an educational channel. You can also find that channel on my LinkedIn page. And once again, thank you for viewing and listening to this content of lot by lot acceptance sampling right here on the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. You all have a wonderful and gracious evening.